My name's Rob Morrison. I'm a senior design team leader at Triumph Motorcycles in Hinckley. So I want to talk to you a little bit today about the latest generation of Bonneville and really how we've designed it and built it, just to give you a bit of an insight into that. My history is I've been with Triumph for 15 years now, just over, full time. I graduated university and went straight to Triumph, but actually I first started at Triumph 18 years ago as a student. I did a year out and had a bit of experience while I was studying, and I've stayed there ever since. It's a fantastic company to work for, and I'm a really enthusiast for Triumph, so hence I'm here now. Design engineers and design team aren't normally allowed out to talk to general members of the public. They lock us away a little bit in case we say things we shouldn't say, or talk about things that are yet to come, because obviously my mind is on projects I'm working on now, which will be out in 1, 2, 3 years time. So this is quite a nice treat for me, actually getting out, meeting people who ride the bike. That's really good. So talking about the Bonneville project, the latest generation of Bonneville, so the 1200 and the 900 we put out. At Triumph we have model codes. I can't use the model codes, they wouldn't mean anything to anyone here, but that's how I get myself out of it and say Bonneville. The first thing to really mention is, when we were told that we were going to be working on this project, there was such a huge recognition. The honour and the privilege it was to be able to work on this. The Bonneville name for Triumph is just so important. It's got so much history behind it. The teams, the engineers we've got involved, I've got engineers ranging between sort of 23-year-olds and 55-year-olds, and they all know the name, they all know the importance, and there was just such a buzz of excitement. It was really quite an exciting time to be involved. That's not me. It is. Obviously, we know where the I'm going to stand on this. We all took it really seriously, basically. You talk about the iconic name, and we know where that iconic name came from. It came from the history of this bike that's been around for so many years, before I was even born, and the importance of it to Triumph customers. If we get this wrong, there's a lot of people we could really upset, and we wouldn't want to do that. Obviously, back in its era, it was a bike to own. It was the bike that film stars wanted to own. It was the bike that teenage tearaways of the era wanted to ride. It was the performance motorcycle. Now, we launched a Bonneville in 2000. So we launched an air-cooled Bonneville, which I've seen quite a few of outside. This basically gave us a reintroduction of the Bonneville into the sort of Hinckley era Triumphs. So in 2006, they all went to the 865cc engine. In 2008, they all went fuel injection. That was it. No more carbureted models for Triumph motorcycles beyond that. In 2009, we introduced cast wheels, and in 2014, we introduced a new church version. It was a special edition, and it really signified towards the end of that model. But what happened in parallel with this is, in about 2013, 2014, there was an explosion of interest. Cool riding culture just took off. It became something that young people suddenly got into again. Modern film stars wanted to ride the bikes. We were approached by footballers, actors, all sorts of people basically approaching us saying, we want to get in on this, we want to be riding these bikes. Suddenly it was the place to be again, it was the scene. So this set the background for us, really. This is running a little bit slow. Come on. Let's try that way. Thank you. Let's try again. There we go. So this set the background, really, with that explosion of interest for us to take on designing a whole new Bonneville. And basically this has been the single biggest project that we have undertaken in Triumph's modern history. There's no other way of putting it. It was 2 engines, it was a 900 and a 1200, and there's further versions of those, different calibrations, different tunes to suit the different bikes. There was 5 completely different chassis. It was liquid cooled, it was going in at Euro 4 emissions. We basically, across the factory, had about 200 people working on this over a period of about 4 years. So, without a doubt, this was the biggest single undertaking we'd taken on. And I want to talk to you a little bit about the engine, because that's my experience. I'm an engine design engineer. I headed up the design team that put this into production. I've got a load of information on the chassis and so on, but it's not my specialism, so I'm going to avoid that, and then I'll hopefully avoid awkward questions I can't answer. One thing that is common across engine and chassis is the sort of process, the route we take. Sorry, I keep on standing in your way, but I can't get it to change. The process we take of actually starting this the whole process. So we're starting with sketches. We're starting with outlines that we've got stylists who draw, who basically say this is roughly what we want it to look like. We turn that into clay models. So the surfaces of the engine covers, the surfaces. Battery's going. Again. I'm going to shout. Yeah, that's fine. Technology. The surfaces of the fuel tank, the surfaces of the engine covers, they're very organic surfaces. So it's not something we want to just create in CAD models in virtual space. It needs to be something that's sculpted by hand and crafted and created. So that's what you're seeing here. You're seeing clay engine surfaces, clay fuel tank surfaces. Where we've got bits of engine that look a little bit more real, that's rapid prototyping. So we've had some bits made in clay, and then we've CAD modelled it, and we've 3D printed them, and started building up a bike with 3D printed parts, and it allows the stylist to carry on working around that in the clay. And we go through lots of iterations of that, where we then scan all the clay, we bring that back into our CAD, we work on getting the surfaces to top quality surfaces, and then we put it back on a bike. The end of that process is we actually end up with a full-size 3D model of a bike that looks like a finished motorcycle. We paint it, we finish it, it looks like a finished product. And we need that, because you need to be able to know that you've got all the details right. While we're doing this, in parallel, these are early screenshots of the CAD models that existed at the time that we were doing this sculpting work, because we're getting straight stuck into the actual engineering behind it to make sure that what we are working on in 3D as something that looks right actually works from an engineering side. So what you're looking at here is a cross-section, well, an engine with the cylinder head and the barrels and the crankcase is removed. This is a cross-section for an inlet port for fuel injector, where there's the fuel injector spray tool. We actually hitting the back of the inlet valves to try and get good optimization of fuel. That level of detail of work is going on while we're still sculpting in clay. It's so important to get the bike right proportions of the bike right. The bike has to look like a Bonneville. It has to look right if you stand back and have expectations. We even changed the bore and stroke of the engine to make sure the proportions of the engine were right when it actually sat there in a frame. So we're going through this whole cycle in parallel. This is just further work. We're doing CFD work on the inlet port, so we're actually looking at where does the gas flow, are we getting good optimization of fuel. We have to do that now because we're trying to hit emissions regulations that are so stringent. You've got to go to this level of design work. This looks complex, but this is actually a computer simulation of the engine, so we can actually simulate it running. And again, this is all being done while we're still sculpting in clay. It looks really simple, but those two orange blobs are the 2 cylinders essentially in terms of what the computer sees. Everything upstream here is intake, throttle bodies, actually 2 exhaust pipes with a balance pipe. All of that is silencers, because silencers are really complex to do in this, but that's just one thing. We then run prototype engines and we correlate this model. So we're basically looking at the data we're running and the data we can collect off rigs with running engines, and we make sure they're actually working. And this is giving us the confidence that the performance of the bike is going to be what we expect to be. So not only are we getting the looks right and the performance right, engineering right, but we know that when we actually got the running engine, it is going to actually work. So then we mature our CAD models a little bit, and this is the sort of CAD model then we'll rapid 3D print and put it back onto that clay bike. And we go through that loop again and again and again with the stylist until we've got something that we believe is going to work as an engineering feasibility
side. Some of the problems we find really early on when we're working on this project, to get the package space right, to get the engine height right. For example, we put a single overhead cam in the engine. We have lots of choice. Most of our engines nowadays are twin overhead cam, direct tacting, that's fairly normal. Where with a single overhead cam with rockers, it gave us the package and the space we wanted. It presented some real headaches from a purely engineering point of view. One of them is, you've got your two spark plugs and they're coming in at an angle into the combustion chambers. And actually, from an engineer's point of view, I don't want that. I want my spark plugs coming in straight. I want to get really good combustion. I want a nice clean combustion. So we were trying to stand them up as tight as we could. And a lot of work went into how short can we make that camshaft, and then the cam cover, and stand those spark plugs up on the end. It's those sort of loops really, really early on in the project that gave us something that actually came together as an engineered package that also looked right. And the sum total of that, what I've overlaid here is, in the sort of brown colour, is the previous generation air-cooled Bonneville engine, so it's a 2000 model. And then in the grey, it's the latest generation 1200. So you've got an 865 in the brown, and you've got a 1200cc engine in the grey. And to basically put it in a simple way, if you were to put a box around the old 865cc engine, the new 1200 engine would fit in that same box with a little bit of wriggle room, a little bit of space to spare. But that was a real headache to do. I'm going to talk you through a couple of areas of the engine now, in a little bit more detail, just in terms of some interesting bits on some of these. So looking, for example, at the what we would term normally the bottom end of the engine, just in terms of crank balancers, rods, pistons, normally go together quite well. One of the things we were looking at for the feel of the bike really early on is the inertia of the engine. So the blue dots on there, this is basically inertia versus the engine capacity, and we've got blue dots at points that we've got confidence if we know they're going to work. And the red star there, that's the 900, that's basically the street twin, that's where we put that nice on this line, we know that is going to work. That's the Bonneville 1200, and where we want to target that one. And that one that looks way off the line is actually the Uttoxeter 1200, where we said we're going to get the same inertia in that engine as we've got on the 900, so we're going to go for the 1200 engine. There's a trade-off there. There's a trade-off in terms of the firing pulses that you feel, how quickly the bike revs up, how well it responds, but it also can give our calibration guys a real headache because they're going to calibrate a bike that's going to be a lot more thumpy, essentially. That's what we made work. A very quick one on balances without getting too much into the maths. Doing the balance calculations on engine is an absolute joy. But that's the arrangement we had on the old 865, I say old, sorry, context to say. 2000 here. Bonneville engine, had twin balancer shafts positioned both on the same, both in the upper crankcase sitting above the crank, and we can calculate how we can resolve the forces in there. Basically, there's always a pitching couple, this blue line that waves up and down there. There's always a pitching couple that you can't fully balance out from that engine. In the new Bonneville engine, we've stuck them 180 degrees either side of the crank, one in the upper crankcase, one in the lower crankcase, and that completely eliminates that pitching couple. And it's getting the chance to do some of these calculations up front before we even style the engine. As we style the engine, it means we can actually get them included. If you take the balancers as they sit on the bike and you chop through the middle of it, you basically see something like that. So what you're looking at here is the crankshaft, and gear that's cut onto the middle of the crankshaft, and then this is the gear that's on the balancer shaft. So there's two gears that mesh right in the middle of the engine. Now, controlling the distance between those gears is quite critical, depending on the grade of gear you achieve. The problem we've got is this gear is cut onto the crankshaft, and it goes through the same process as we make the crankshaft, so it gets the same heat treatment in the drive, for example, and you get some distortion of the gear teeth. So what we want to do is we want to have a bit of adjustability in there, so that you can actually set each bike to get that meshing contact right, so you don't have the rattle engine, you don't have the winding engine. And the way we did that is this red shaft that the balancer runs on is actually eccentric. It's not got bearing surfaces that the gear runs on, where it mounts into the crankcases aren't actually coaxial, they're offset. What it means is if you turn this shaft, if you stick an Allen key in the end and turn it, you move the gear closer or further away from the crankshaft, so you can actually adjust that distance. And then on the bike itself, you've actually got inspection cover and a bolt on top of the bike. Those two. those two on the cab. So if you take them off, if you get in through that hole that you've just taken the bolt off from the top, you get access to the clamp, and you can undo the clamp, and then you can go in through the hole that's behind the inspection cover. You actually get straight onto the end of this. So you can actually set that up on a finished motorcycle, you can actually set it up with the engine running. Now we've got some calibrated tools on the end of our assembly line, so we don't need to run the engines to set that, but that can be adjusted. So if the dealer, for example, later on is changing parts in and out, changing a balancer, for example, they can reset that, and they can actually set it on a running bike and actually tune the noise to get it to absolutely spot on. And you can do the same with both of the two balancers. A little bit on the cylinder head and cam drive. So the photo on the left here is actually taken from the sectioned engine that's sitting around the corner, so feel free to go and have a look at that later on. It's quite fun creating that. Basically we've got, as I say, single overhead cam with rockers on the inlet and the exhaust side, but there were some quite fun tricks to be able to play on this. One of them was lubrication. It needed quite a bit of lubrication to get that all to work. So the cam frames sit down and hold that all in place, and the bolts that hold that, they actually form part of an oar circuit that runs up one side, along the shaft, back down, around the camshaft, back up and along. And it lubricates the actual point at which the rockers run on the shaft, but it also lubricates the contact between the bearings and the cam, and also the rockers on the end of the valve. And then the bearings themselves, so these are the bearings that run on the rocker, actually contact the camshaft. Again, there was a lot of work done on this. You'd think it was just a bearing, but actually, if you've got a bearing running on a flat surface and there's any sort of misalignment at all, what you can actually end up with is loading a bearing really, really badly. You're going to get an edge loading on a bearing, and that's not going to work. So the profile on the end of these bearings has actually got a little bit of crowning. It's a logarithmic crowning. These are special bearings made by the bearing company before us, and it allows for this any slight misalignment might just get tolerance to making the parts. It gives you that durability. We didn't know any of this before we started this project, because we've not done one of these as a modern Hinkley era Triumph. So this is all a great learning process for us. Again, this looks a little bit complex, but it's showing again the level of simulation we go to try and work out the problems we're going to see before we even build an engine and try and eliminate it. So this is a simulation model of the valve train. You can actually see camshaft, rockers, and then it represents the contacts with valves, valve springs, and so on. And from that, we can generate the forces that are in the part, and we can put that into a final element analysis package. But basically looking at the stress that's in the rockers. You can see stress distributions. This was an early iteration. There was a point there that was saying, well, if you run with that design, you're going to have really high stress, and it is going to break. And then we're able to wash that out with one design that's safe. We're doing this well ahead of ever having released a part or even seen a part. We do the same with the valve springs. We can even look at the dynamics of the valve springs to make sure that with various different cam profiles we want to run, they're actually always going to work. So we can run a slightly different model that's even more complex, and from that we generate these sort of curves. This is just a typical valve. A set of valve lifting curves. So you look at your exhaust valve lifting and an inlet valve lifting, and you can see there's a little bit of overlap. So one valve is starting to open before the other one's finished closing. That's fairly normal. You're looking at actually what's the velocity of the valve, then you start looking at acceleration, you start looking at stresses, and again that means we can actually design all these parts and have confidence when we build our first ever engine. Hopefully should at least work to some degree out of the box, and then all we've got to do is a little bit of development and tuning. We're not actually trying to design things with very expensive parts around us. A little bit about the cam profile itself. On the cam lobes, because of the geometry we get with the rocker, we actually need to drive. Everyone's used to seeing what a cam lobe looks like normally. It's a nice egg shape. Actually, this has got I'm trying to think of the right word for it. It's got a profile that inverts on itself. So it's not just a positive profile around it, it actually cuts in on itself. Well, you can see that to actually grind that, you've got to have a grinding wheel that's smaller than the radius of whatever that is. So in actual fact, to grind these, we actually had to have a 40mm diameter grinding tool. So before we can even design the engine to this level, we're talking to our guys in our machine shops, because these are all made in-house, and they're saying, can you get this equipment? Can you do this? And it's a big collaborative project across the whole of Triumph to actually say, yeah, okay, we're going to commit to that, we're going to ask for something that, initially they weren't that keen on. We've also got decompressors fitted to the 1200s, not 900s, we did need 1200s, the compression is just too much. You have to get around it by putting bigger and bigger starting pressure on, bigger batteries. We don't want to be loading that weight inside that. So we put the decompressor on, and the main reason why I'm showing that is this is one of the few things, we don't normally do this, but this is one of the few things we've actually patented because it's such an intricate little device that managed to fit in there. And no one else has actually managed to do this for decompressing basically both cylinders with a single device on the middle of the camshaft. And basically what you're looking at here is cylinder pressure as you're trying to crank the engine. That's what it would be, and that's what we knock it down to. So we've managed to tune that. And basically it's a centrifugal device. So you've just got an arm that flings out when the engine starts going faster and basically pulls in the compressing unit basically in from the low one camshaft. So it's quite simple from how to implement, but it's again set up. While we're on the top end, I mentioned FEA final analysis. It's a tool we use to calculate stress and whether something's going to have a problem with the fatigue line, for example. We don't just do that on the individual components, we do that on the bike as an assembly as well. So what you're looking at here is a full engine, essentially crankcase, barrel, cylinder head, all meshed, and in a frame, because obviously you're not seeing any loads when it's actually in a bike. And then we can actually look at it under running conditions, and we can see where you're seeing stresses. We can simulate not just the engine running flat out or over a juice cycle, we can simulate things that might go wrong, like what happens if you ride into a curb at 30 miles an hour. That's obviously going to cause damage maybe to your front wheel and your forks, but it's going to put stress on your front engine mounts as well. And what's going to be the consequence of that? And we factor all of that in as we go through the design stage. And again, and that's just a cylinder head gasket from the bike. We can even use this stress analysis to see what's the distribution of force we've got across the cylinder head gasket. Have we got an even distribution of force? Are we always going to be sealing? Or are we going to have problems? And again, if we design our cylinder head gaskets, before we've ever run an engine, basically when we do our testing for that, when we're running an engine, what we're really trying to do is confirmation testing. We're trying to develop it, we're trying to prove it off, prove that it's good. This is a simulation of the cylinder head being cast. So it's a gravity cast, so the aluminium is literally just being poured in under the weight of gravity. That's how it goes. I think total time to cast one of those is about 15 seconds to fill them off with aluminium. It's really useful to do this sort of analysis because what we can then look at is the quality of the castings that we're going to get. We can see, are we trapping air in any places? Do we need to redesign the part or the tooling to make the parts so that we're getting good, consistent, reliable parts? We then take those parts and we scan them, we 3D scan them, and we can compare back to the CAD. So this is just a comparison of an actual first off cylinder head that we have for the project against the CAD data, saying where's the difference. Not only that, we do CT scans of those parts, so we can look at every single section through that and say, is everything inside exactly where we'd expect it to be? And for example, a little bit indistinct, but the red outline is basically showing what it should be, and the grey is showing what it was, and we found that, oh look, we drilled a hole a couple of millimetres too deep. It's just a good way of catching all of that stuff. If we ever run an engine, again, if we blow an engine up when we're testing first off engine, it's really expensive. It's better never to get to that stage. In terms of the casting process, it gets a whole lot more fun when you start talking about crankcases. Because crankcases are high pressure die cast. So this is the first ever casting we had for the new Bonnevilles. This is actually a meeting we're having. We're sitting around looking at it, trying to work out, is everything okay? But in terms of the design for that and the tooling for that, the tooling is very big and complex. It's consisting of lots of different parts, all machined out of high-grade steel, which is then heat treated. They're put together in these rather large frames. That's about my height, just to put it in reference. Great big hooks to actually lift these things around and put them into high-pressure die casting machines, which you wouldn't fit height-wise in this room. This is our factory. We high-pressure die cast these ourselves. So this is an in-house process that we have full control over. So that's tipping blocks of aluminium to molten metal coming out the bottom. That's one of our high pressure die casting machines. And then it's pouring the molten metal into basically a chute where it gets ready to be forced in under a lot of high pressure. So this unit here, it's got a great big hydraulic ram, and that is going to push the metal into the tool. That's the tool. It's just being cleaned. It gets some dye release agent sprayed in it, and the actual high pressure die casting is that, and it's done. It's that quick to actually inject metal and end up with a cast part. So here he goes in with his rather large lifting arms, one because it's heavy, second because it's hot. And there is our, that's another crankcase from the Bonneville 1200. Essentially, that's that. And that's your runner in, and that's letting some metal get out the end to make sure you actually fully fill the mould. And again, we simulate this, and we look at this in quite a lot of detail. So, running in the top left is just watching the metal fill through. Again, this is before we even cut the tooling to make sure we're designing the tooling right. And we can see how it fills, and we can change the design accordingly to make sure we're down with a good part. We can watch where the metal goes, and we can even look at the velocity of the metal in there, because you'll end up with a bit of tool erosion. It's worth saying, the whole process of filling from there to right at the back, it takes, I think on this one, it's about 0.7 of a second to inject that metal in there. Where you're seeing these areas at the front, with the sort of yellow colours on terms of the speed, the molten metal there is moving, I think about 145 miles an hour through the tool. So that tool's got to be pretty durable to deal with that. It's hot and it's being pushed in fast. A little bit about the barrels. So the barrels on the 1200 were, again, a nice learning curve for us. It was an interesting one to get involved with. So normally you get your barrels like that, and the manufacturing process, again, they're usually gravity die cast, and they're honed, machined, and that's great, put them in the bike. What we found with this is, if you hone a set of barrels, you can then take them away and you can measure and say, how round are they? You know, how true have we got that machining? And that's a plot on the top left. That's just basically taking it apart, measuring it. Great, we've honed it, and yes, we've got something that's round. When you bolt it up in an engine, you get that. That's an exaggerated plot, but it's, you know, that's basically what we're looking at. We're basically that's distorted completely out of round. And that's not going to be particularly good for durability of the piston rings, and it's certainly not good for things like oil consumption and blow-by. Not what we want. So we got round that. We basically we looked at the section at the top of the crankcase, and we replicated it. We took a section of the head, and we replicated it. And we bolt those two things together around the barrels before we do the honing. So what you're doing is you're distorting the part as if it was fitted, and then you're honing it in that condition. What it means is then when you take that barrel and just take it and measure the roundness, you get something that looks completely wrong. It's actually not right, it's not round. When you bolt it back in an engine, you get a lot closer to a true round barrel. We tested this, that's the two conditions, the oranges if you didn't use what we call honing glasses, and the blues if you do. And that's the blow-by from the engine. So you can see it, I mean that's at a given engine speed, about 6,000 RPM. We've significantly reduced the amount of blow-by in the engine by introducing this process. It's not something we've done on any Triumph before, it's new for this model. So we're going to a bit of a learning curve for us. A little bit about clutch gearbox. Again, gearbox, we've got a 6-speed gearbox on the Bonneville, 5-speed on the 900s. Again, we use computer simulation, even at the design stage of these gears. We can look at the loading you get, the distortion you get in the gears, and make sure you get a nice, good spread of contact. You're not going to lead to things like pitting or premature wear on the gears. But you can also study it from the point of view, make sure we don't end up with noise coming from it, and actually design them so that when they deflect at the right sort of load you'll be riding at, it's got the right contact patch for that load. So they'll run best under load, essentially. And then the clutch itself is a slip and assist clutch. Now, anyone who's been involved in racing will know about slip clutches, but that wasn't why we wanted to introduce it to the bike. It's the assist function we were really interested in. So, on a slip clutch, basically when you overrun the bike, when you close down the throttle, for example, in the rev quite high, it allows the clutch plates to push apart and allows your clutch to slip. In a slip and assist clutch, you actually get the same thing going the other way. So when you put your clutch under load, when you accelerate hard in a gear, the plates pull together. These ramps actually pull your clutch pack closer together. The advantage of that is we don't need some big clutch springs to actually pull the clutch plates together to give you your traction between the clutch pack, which basically means your clutch lever effort is a lot lighter. If we remove that and just had to rely on the springs, we'd have a much heavier clutch action. You know, a 1200cc twin-cylinder bike is going to use a pretty heavy clutch. And then a little bit about cooling, because liquid cooling, this was a thing that was much debated before we went ahead with it. One of the objectives we were given is really try and make it hidden on the bike, as best you can. You've got a radiator, you can't hide a radiator, it's a radiator. You can hide it somewhere and no one sees it, it doesn't work, because you kind of need airflow through. But what we were very pleased about is we basically built a cooling system with everything inside the bike. The water pumps inside the bike, half of the coolant passageways up to the back of the barrels are inside the bike or built into the barrels in correct cases. There was only 2 coolant hoses on the outside of the bike. Net result there on the crux and the misleading gears, it blends in reasonably well. With this radiator where we have an oil cooler, we've done our best to sort of minimise the impact of that, and actually it's been really positively received, so we're really pleased with that. Again, we're using simulation tools really early on. You're looking here at the coolant flow up from the bottom of the pump, it goes in through the barrels at the back, then it goes over the head and out the coolant hose at the top of the engine, through the thermostat and into the radiator. This serves quite a few purposes for us, having this sort of data. So, okay, we can look at that in terms of velocity, which is what that is, how fast the coolant is flowing. We can look at it in terms of pressure, which is really useful to us, because we can actually then say, well, how do we get to be more efficient? What's stopping this coolant flow from going? We're getting it flowing in the right places. But then we can also look at it in terms of temperature. We can make sure we're taking temperature out of the head and out of the barrels in the right places. This temperature data goes all the way back into the structural FE analysis that we did at the beginning. So when we're doing our structural finite analysis of the cylinder head, for example, we're able to put accurate temperatures of the material, because the material properties will change that temperature. So it's again part of that cycle. This is something that has never seen the light of day, and no one outside Triumph normally sees this. So this is one of the 2008 Bonnevilles, which is obviously air-cooled, but we converted this to be a liquid-cooled bike as a one-off project ahead of doing the new Bonneville. So we built a one-off cylinder head with water cooling. We're running a water pump off the side of the crank outside on the covers, and we put that in a climatic wind tunnel, and we tested and verified that we're getting the right amount of cooling on one of these bikes up front. Again, it's really important to know that we're going to be able to size the radiator adequately and not make it bigger than we need to right at the start of the project. And a little bit about the exhaust system, because I know the guys on the team that did this, my team, were exceptionally proud of what we managed on the exhaust system. So, basically, it's a modern bike, it's got to pass Euro 4 emissions, basically it's got to have a big catalyst in there. So what we've got is what looks like 2 pipes, but actually the exhaust gases come in, they actually mix together in the front of the cat box, they go through a catalyst and they separate out and go back out on each side. And then we complete the look, this is on the Uttoxeter, by having a cover on either side so it looks like you've got a continuous exhaust run going down the side of the bike. So on a Uttoxeter, you get that, it looks like a continuous flowing exhaust run, but there's a couple of covers there. On the 1200 Bonneville, we were able to go a stage further, and this is what we were really proud about. It really annoyed our manufacturing guys, our workshop team. They did a fantastic job. They weren't pleased with the idea. So on the 1200 Bonneville, you have got an unbroken run of pipe all around the outside. And we've done that by having twin skid headers, so you don't get bluing and stuff like that. You've got an inside pipe and an outside pipe. Basically what you do is you put one pipe inside another, fill the gap between them with shot, and then you bend them together, and then you empty all the shot out afterwards, and that maintains the gap between the 2 pipes. And then what we do is we take that bent 2 pipes, and we laser cut the inside pipe and weld it to it, so take the flow off inside, then we bring it back out again, and we leave the outside pipe still intact on the outside, so we don't have to break that flow. So that's essentially what we've got, and this is why the guys responsible for the laser cutting, which really didn't like it. So what they actually have to do is they have to come in and they have to laser cut the outside pipe, take the piece out, put it back on the laser cutting machine, laser cut the inside pipe, and then they take that out and then they can weld this thing in. But the bit of pipe on the inside that we've removed, we actually reuse that to make that bit of the pipe later on, so we're not wasting material. What we've got there is a couple of processes. So this is bending two pipes together. Stick your arm in them. They don't really seem to notice that you've got two steel pipes, one inside another, being bent, and they move quite easily. They go through a brushing process, so they're going to be brushed at the end after they've been welded and after they've been laser cut. But if we find that if we do it in stages as we go as well, you can keep the quality of the finish throughout the process. So we've just got a nice machine that does that for us as we go. And then the really fun bit, which is the laser cutting. And these things are kind of hypnotic. I understand that a laser cutter to do that. There was even quite a lot of work in tuning the strength of the laser, because you need to cleanly cut the outside pipe and you don't want to cut the inside pipe. Otherwise you have exhaust gas leaking. So it was really quite a lot of fun for everyone in the factory trying to get this thing to work. Yes, they are. Yeah. And then afterwards, this is part of my long process for everything we're actually making in-house. We've got checking fixtures and the types of characters if they're fitted to a motorcycle. We've got checks to make sure did that cut go in the right place, did that cut go in the right place. Making sure everything's right. Change the section we want to weld into. And then again, off they go. And he's having to actually weld a casting onto the inside piece of pipe with only a small opening to work through. So it's really quite a skilled job. And again, it's fantastic watching these guys work. So that is the finished result in terms of the Bonneville 1200. You end up with an unbroken pipe on the outside, but that isn't what's actually happening. And again, on the section engine that's just round the corner, you can kind of see that there's a catwalk to cut open, and you can have a quick nose and you actually see what that's doing. So, just in terms of where we ended up, we've done all this simulation, we've done it all, we've got the engine, we've got our first engine on the rig, and we very carefully said what we wanted to achieve, and we were really pleased we basically nailed exactly where we wanted to be. So we had the street spin, the 900, we had the Bonneville 1200, and then we had the Structure 1200, which was pretty much the same torque, which is more top end power. And quite different feels, quite different sounds coming from each of the engines. In terms of differences then, we obviously had variations about different capacities, different inertias, different compression ratio, different calibrations for all the lights, different exhaust systems, a 5-speed gearbox and a 6-speed gearbox, with different final gears on the lights. And we also got different exhaust systems, all with different sizes as well. All of this work I'm talking about is still handled by this one design team. This is a group of about 16, 17 guys. So they've got a lot on their plate each. And of course, all different variations on finishes, brushing colours, painting colours, so on. And then very quickly, just some shots from the actual launch video. This was in December 2015, I can't remember now. It was an event in London, and it's not the sort of thing we would have normally done, but it was such an important point for us, and it was such a satisfaction of having delivered this at the end. They put on a big launch event, they invited a lot of journalists along, a lot of riders and racers and stuff like that, and we had a full weekend of it. We then did the full actual white launches, which is a fairly normal process where you take your journalists out and go somewhere, explain things in this instance, so everyone can get out and ride bikes and hopefully write glowing reviews. And then basically just some extracts of what we had at the time, because obviously all the team was being press, and we were just really pleased with the reception that I got. And I think that was one we were really proud of. It was kind of like the pressure on us to deliver something that would be known as a Bonneville, and have it received well. That was just such an immense deal. So that was it. I've rattled through as quick as I can, but hopefully giving you a bit of an insight into what we do in the factory. And if anyone's got any questions about this, just grab me, and I'll be happy to answer.
Thank you.